So let's get ready to ace the AWS Certified Solution Architect Associate exam with our comprehensive crash course. So let's cover some compute services in AWS, Elastic Compute Cloud EC2, Elastic Container Service ECS, Elastic Container Registry ECR, Elastic Container Service for Kubernetes EKS, AWS Elastic Beanstalk, AWS Lambda, and AWS Batch. So master these essential compute services for the exam. Let's dive into the world of Amazon Elastic Compute Cloud or EC2. Let's explore the key components of these essential AWS service. Amazon Machine Images. First up, let's talk about Amazon Machine Images or AMIs. These are pre-configured templates that allow you to quickly launch new EC2 instances based on specific configurations. With a wide range of operating system and applications, AMIs are the foundation of your EC2 instances. Once you have selected your AMI, it's time to choose an instance type. These defines the size and parameters of your instance, including CPUs, memory, storage, and network performance. The flexibility to choose from different instance families ensures optimal performance of your applications. Now let's explore the various purchasing options for EC2 instances. From on-demand instances to reserved instances and spot instances, each option is designed to help you optimize cost based on your deployment needs. Lastly, whether it's shared tenancy by default or dedicated tenancy for specific security and compliance requirements, understanding tenancy is crucial when launching your EC2 instances. Let's dive into Amazon EC2 Container Service, also known as Amazon ECS. Amazon ECS allows you to run Docker-enabled applications packaged as containers across a cluster of EC2 instances without the need to manage a complex cluster management system. AWS Fargate abstracts the burden of managing your own cluster management system, while Docker automates the installation and distribution of applications inside Linux containers. Containers are portable, lightweight, and scalable across a cloud environment, ensuring applications run as expected regardless of deployment location. So choose between Fargate Launch for simplicity or EC2 Launch for greater customization and control over parameters. AWS CloudWatch monitors metrics against your containers and clusters, allowing for easy creation of alarm based on specific events. Amazon ECS clusters are dynamically scaled within a single region, allowing for deployment based on resource and availability requirements. So let's dive into the Elastic Container Registry, or ECR, is a fully managed service provided by AWS. It offers a secure and centralized location for developers to store and manage their Docker images. This service seamlessly integrates with the EC2 container service, providing a hassle-free solution for distributing and deploying Docker images across applications. ECR eliminates the need for developers to provision infrastructure as AWS manages the entire process. It empowers developers to efficiently push, pull, and manage their Docker image library in a secure environment. Now let's dive into Elastic Container Service for Kubernetes, also known as EKS. Kubernetes is an open source container orchestration tool designed to automate, deploy, scale, and operate containerized applications. It's capable of managing tens, thousands, or even millions of containers, and it's container runtime agnostic, meaning it can run both Rocket and Docker containers. EKS is managed service provided by AWS, allowing you to run Kubernetes across your AWS infrastructure without having to manage the Kubernetes control plane. You only need to provision and maintain the worker nodes. So let's see how the Kubernetes control plane works. Let's dive into and understand the key components that make it all happen. The Kubernetes control plane consists of various components such as different APIs, kubelet process, and the Kubernetes master. These components are responsible for facilitating communication within your cluster and managing the schedule of containers onto nodes based on their compute requirements. In EKS, AWS takes charge of provisioning, scaling, and managing the control plane. They ensure resilience by utilizing multiple availability zones. These means your control plane is in good hands, allowing you to focus on your applications. In Kubernetes, worker nodes are the backbone of your cluster, responsible for running containers managed by the control plane. Each node is an on-demand EC2 instance equipped with Docker, kubelets, and AWS IAM Authenticator for security as a customer. Managing these nodes within EKS is crucial. Once provisioned, the worker nodes seamlessly connect to EKS using an endpoint. So let's learn about AWS Elastic Beanstalk, which is an AWS managed service that simplifies the process of deploying and scaling web applications. It allows you to upload your source code and configure the environment, while it takes care of provisioning and deploying the necessary AWS resources such as EC2 instances, auto-scaling groups, RDS database instances, and Elastic load balancers. For developers and engineers who may not have extensive AWS experience, Elastic Beanstalk provides a straightforward solution for deploying, provisioning, monitoring, and scaling web applications. It's a quick and effective way to get your applications up and running without the need for in-depth infrastructure management. With AWS Elastic Beanstalk, deploying web applications become a seamless process, allowing you to focus on your code and application functionality. So let's dive into a quick overview of AWS Batch. AWS Batch is designed to manage and run batch computing workloads within AWS. It's ideal for tasks like training machine learning models or conducting large-scale data analysis. In a cloud environment, maintaining a batch computing system can be complex and costly. However, with AWS Batch, you can seamlessly create a cluster of compute resources that's highly scalable and takes advantage of the elasticity of AWS. With AWS Batch, AWS handles all the provisioning, monitoring, maintenance, and management of your clusters, making it a powerful and efficient tool for batch processing. Some of the key components of AWS Batch are: the first component is a job, representing a unit of work to be run. These could be a Linux executable file, a Docker container image, or a shell script. Jobs run as containerized applications, which you can choose to run on AWS Fargate, EC2 resources, or an Amazon EKS cluster. In most cases, Fargate is the ideal choice as it allows AWS to handle all infrastructure specifics. However, larger scale jobs are those requiring specific architecture or direct access to processors or GPUs may need EC2 main instances. You can set up references and dependencies between jobs, allowing you to wait until one job is finished before starting the next one. Jobs can be various states, including submitted, pending, running, and failed. Have you ever wondered how to seamlessly integrate your on-premises environment with the AWS cloud? Let's dive into the world of AWS Outpost. AWS Outpost is all about bringing the capabilities of the AWS cloud to your on-premises data center. It allows you to use native AWS services, tools, and APIs within your local infrastructure, offering a consistent hybrid cloud experience. Outposts are available as 1U or 2U rack mountable servers or as entire 42U racks that can be scaled to deployments of up to 96 racks. AWS is responsible for securing the Outpost rack infrastructure, while customers are responsible for securing the applications they run on Outpost. Outpost may be connected to AWS using either a direct connect or VPN connection, ensuring a secure and reliable link to the AWS cloud. So whether it's for latency, security, or governance requirements, AWS Outpost provides the bridge between your on-premises environment and the AWS cloud, offering a seamless hybrid cloud solution. AWS Outposts offer a range of services including ECS, EKS, S3, RDS, and EMR, all available on premises. Customers can securely connect to other services and resources using private link gateway endpoints such as DynamoDB. Additionally, Outposts support EC2 with various instance types like M5, C5, and R5, along with storage options for EBS volumes, local disk, and local instance storage. Outposts enable migration and disaster recovery scenarios through Cloud Endure, allowing workloads to fail over in the event of an outage. It also supports VMware Cloud on AWS, providing a secure and scalable hybrid cloud infrastructure. Plus, AWS manages patch updates, eliminating the need for manual maintenance. Customers can conveniently order Outposts through the AWS Management Console, selecting from different compute and storage options based on their requirements. It's important to note that an enterprise or enterprise on-ramp support plan with AWS is required to place an order. In AWS, there's EC2 auto scaling for scaling the EC2 fleet and an auto scaling service for Amazon ECS tasks, DynamoDB tables, and Amazon Aurora replicas. Let's consider a scenario where a single EC2 instance acts as a web server. As the demand increases, the CPU utilization rises, requiring additional processing power. With auto scaling, a metric can be configured to automatically launch a second instance when the CPU utilization reaches a certain threshold, ensuring load balancing and optimal performance. Auto scaling offers automation, greater customer satisfaction, and cost reduction. It automates provisioning based on custom defined thresholds, ensuring elastic resource provisioning. These prevents manual deployment and removal of resources. It also enhances customer satisfaction by preventing performance issues during demand spikes and reduce cost by automatically scaling resource based on demand. Let's dive into the complexities and different methods of autoscaling to ensure how architecture's performance is now top-notch. Autoscaling is the glue that makes the well-oiled machine work, allowing you to manipulate and modify the number of instances within an autoscaling group in four different ways. First, you can manually adjust the variables, then schedule scaling to happen at certain times of the day. There's also dynamic scaling, which is automatic, and finally, predictive scaling, utilizing machine learning to provision instances based on training data. Each method has its pros and cons, and understanding when and where they have their place is crucial for a fault tolerance architecture. Manual scaling. When you know a traffic spike is coming, manual scaling lets you proactively adjust your fleet size, reducing downtime for users and ensuring a smooth experience. However, it's not a scalable solution for everyday use. It's best suited for rare, planned events, not long term management. So, while manual scaling can be a lifesaver for those unexpected traffic surges, auto scaling remains the go to for day two operations. While predictive scaling aims to anticipate load increases, provisioning new instances before they are needed. This is achieved through machine learning, which learns traffic patterns and adjusts scaling accordingly. Ideal for cycling and recurring workloads, predictive scaling is effective for traffic patterns such as normal business hours or batch processing. It utilizes historical data from CloudWatch, creating daily forecasts based on recent metrics. Test predictive autoscaling in forecast only mode to see its predictions without taking any actions. Evaluate the forecast and compare it to actual data using the EC2 autoscaling console. So consider using both predictive autoscaling and dynamic autoscaling simultaneously for a comprehensive approach. While this may increase cost, it can enhance user experience and ensure high availability. If you're looking to optimize your cloud architecture, time-based or scheduling scaling is a game changer. Scheduled scaling allows you to add or remove instances from your autoscaling group based on specific time parameters. For instance, you can schedule the batch processing instances to come online during off-peak hours when spot instances prices are lower, saving your money. Scheduled scaling is a powerful tool for cost reduction. By turning off dev environments after business hours and scheduling them to turn back on in the morning, you can avoid unnecessary instance usage. This approach not only saves cost but also promotes efficiency by ensuring resources are only active when needed. You can even combine scheduled scaling with dynamic scaling for maximum efficiency. For example, you can have dev and test environments set to turn and on and off at specific times, while using dynamic scaling during the day to adjust the number of instances based on workload requirements. So by leveraging scheduled scaling, you can significantly reduce cost and optimize resource usage within your cloud architecture. So let's dive into AWS Elastic Load Balancer service. The main function of an Elastic Load Balancer or ELB is to evenly distribute inbound requests across a group of targets, such as EC2 instances, Lambda functions, IP addresses, or containers. Using an ELB strengthens infrastructure, helps with unpredictable spikes, traffic spikes, and provides high availability. It automatically scales to meet incoming traffic. There are three types of ELBs: application load balancer, network load balancer, and classic load balancer, each with specific features and use cases. Listeners, target groups, rules, and health checks are essential components of an AWS ELB, ensuring efficient routing and resource management. By understanding the AWS Elastic Load Balancer service, you can optimize your infrastructure for better performance and resilience. So let's do a short overview of server certificates. The application load balancer provides a flexible feature set for web applications running the HTTP or HTTPS protocols. When using HTTPS as a listener, additional configurations is required. So to recycle encrypted traffic over HTTPS, the ALB needs a server certificate and an associated security policy. The server certificates used by the ALB are X.509 certificates provisioned by a certificate authority, such as the AWS Certificate Manager service. When selecting HTTPS as your listener, you can choose a certificate from ACM, upload a certificate to ACM, choose a certificate from IAM, or upload a certificate to IAM. ACM simplifies the configuration process and is the preferred option. If deploying ELBs in regions not supported by ACM, you can use a third-party certificate by using IAM as your certificate manager. These adds flexibility for third-party certificates. So let's understand the application load balancer in AWS. The ALB operates at layer 7, the application layer of the OSI model. It provides advanced routing and visibility features for application architecture such as microservices and containers when used in HTTP or HTTPS. Before configuring your ALB, it's good practice to set up your target groups. A target group is simply a group of resources that you want your ALB to route requests to. To create a target group, go to the EC2 service, select load balancing, then target groups. Configure the target group settings, including the target type, protocol, VPC, and health check settings. To create an application load balancer, go to the AWS Management Console, select Load Balancing, then Load Balancers. Follow the steps to configure the ALB, including setting up listeners, availability zones, security settings, and associating target groups. The ALB in AWS provides a flexible feature set for advanced routing and visibility features. So by understanding how to configure target groups and create an ALB, you can effectively manage and optimize your application architectures. Now let's dive into Network Load Balancer in AWS. It's a powerful tool for balancing incoming traffic to your target groups. Unlike the application load balancer, the NLB operates at layer 4 of the OSI model, balancing requests based on TCP and UDP protocols. These makes it an excellent choice for application running ultra high performance and a static IP address. Now let's walk through the process of setting up a network load balancer in the AWS Management Console. First, navigate to EC2 under Compute, then under Load Balancing, click Load Balancers, select Create Load Balancers and choose Network Load Balancer. Configure the listener, availability zones, security settings, routing, and target group. Once everything's set, click Create to provision your network load balancer. With the NLP, you can efficiently manage and balance incoming traffic, ensuring high performance and reliability for your applications. Let's have a quick understanding of Classic Load Balancer in AWS. The Classic Load Balancer supports TCP, SSL, TLS, HTTP, and HTTPS protocols. It's best practice to use the ALB over the Classic Load Balancer unless you have an existing application running in the EC2 Classic network. To create a Classic Load Balancer, go to EC2, then Load Balancers and select Create. Configure the listener, availability zones, security groups, health checks, and associate instances. The Classic Load Balancer offers support for EC2 Classic, TCP, and SSL listeners, and sticky sessions using application generated cookies. Let's explore the crucial relationship between ELBs and EC2 autoscaling. ELB and EC2 autoscaling are essential for optimal efficiency, providing dynamic load management and elastic scaling based on demand. Each service solves specific operational challenges, but when combined, they work seamlessly to manage and scale EC2 compute resources. Without autoscaling, an ELB requires manual management of resource targets based on demand, creating operational burdens. Conversely, without an ELB, autoscaling struggles to evenly distribute traffic to the EC2 fleet, leading to inefficiencies. So by associating an ELB with an autoscaling group, the ELB automatically detects instances and distributes traffic, ensuring efficient resource utilization. Are you curious about how AWS services are driven by customer needs? Let's take a closer look at the customer driven innovation behind the AWS Gateway Load Balancer service. The AWS Gateway Load Balancer service is a prime example of customer driven innovation. Customers face challenges with the deployment process and scaling for virtual appliances, leading to the development of these essential features. Two key features were identified as essential for the AWS Gateway Load Balancer service. The first is VPC ingress routing for the Internet Gateway, allowing traffic to be forwarded to a gateway load balancer by updating route table in a VPC. The second feature addresses IP tunneling to ensure seamless traffic redirection without interrupting normal flow and interactions. The gateway load balancer provides a single point of access for all inbound and outbound traffic, enabling seamless scaling of virtual appliances based on demand. It also allows for the addition of custom logic into any networking path in AWS, providing flexibility and control. In conclusion, the AWS Gateway Load Balancer service exemplifies how customers' needs drive innovation, resulting in scalable, flexible, and transparent solutions for managing network traffic. Ever wondered how the gateway load balancer and Genie protocol work together to protect your network traffic? Let's dive in and break it down. The gateway load balancer consists of two parts: the VPC gateway load balancer endpoint and the actual gateway load balancer. The VPC gateway load balancer endpoint is defined in the VPC to protect the traffic, while the gateway load balancer sends traffic to a fleet of EC2 instances running third party network appliance software. To make this happen, the gateway load balancer uses the Geneve tunneling protocol. Geneve creates a layer 2 logical network encapsulated in UDP packets, providing extensibility and leveraging network interface cards for performance improvement. A tunnel is established between the gateway load balancer and the fleet of instances on the backend. Traffic is encapsulated and sent through the tunnel to the security appliances implemented in EC2 instances, which examine and act on the packets. Geneve uses port 6081 for traffic and HTTP port 80 for health checks. And that's how the gateway load balancer and Geneve protocol work together to ensure the security and smooth flow of your network traffic. Introducing the gateway load balancer. The gateway load balancer endpoint GWLBE is defined in its own subnet per availability zone. It can be added to a route table as the next hop and integrated into the traffic flow of a VPC. The gateway load balancer endpoint operates across multiple accounts and VPCs with centralized control and administration. It's similar to AWS Private Link and plays a crucial role in integrating the security VPC into the traffic flow. To set up a gateway load balancer, provisioning a dedicated VPC and third-party virtual appliance software on EC2 instances. Then provision the gateway load balancer and target groups similar to other Elastic load balancers. The gateway load balancer endpoints are created in dedicated subnets, updating route tables to integrate them into the traffic flow. So what's the deal with serverless compute? Well, to really understand it, you have to first understand servers. Imagine all the work that goes into running an EC2 instance, installing software, patching, scaling, and more. Now think about that maintenance and administration going away, allowing you to focus solely on your code and business logic. That's the idea behind serverless. So let's focus on AWS Lambda. It's made up of functions representing your business logic, and you can configure important details like permissions and power allocation. To upload your code, you can write it directly in the service or upload via a zip file on or Amazon S3. The programming language must match the runtime you select. So let's fully understand AWS Lambda. AWS Lambda supports several runtimes like Java, Go, Node.js, C Sharp, Python, and Ruby. If you want to use a language not on that list, you can bring other languages using the custom runtime API. This feature allows running PHP or C in Lambda. Your function can be invoked directly through the console, SDK, AWS toolkits, or CLI. It can also be invoked using a function, URL, an HTTP endpoint, or automatically by trigger like an AWS service or resource. Once triggered, your Lambda function can make calls to downstream resources like Amazon DynamoDB, Amazon SQS, and Amazon SNS. The server automatically monitors your function through logs and metrics, and you only pay for what you use, request duration, and compute power provisioned. So with AWS Lambda, you have the flexibility to choose your runtime, various invocation methods, and you only pay for what you use. Looking to invoke a Lambda function but not sure how? Let's explore the different ways you can do it. You can invoke a Lambda function directly using the console, CLI, SDKs, or automatically using a trigger like an AWS service. For synchronous invocations, you can use the request response model, perfect for maintaining order and waiting for a response. The asynchronous model, also known as the event-based model, is ideal for running functions that don't need to wait for a response. It offers automatic retries and a built-in queue. Lastly, the stream model or poll-based model, it great for processing messages from stream or queue-based services like DynamoDB Streams or Amazon SQS. So whether it's synchronous, asynchronous, or stream-based, there's a Lambda invocation method that's right for your specific use case. Let's dive into monitoring and troubleshooting with AWS Lambda. When it comes to monitoring and troubleshooting with Lambda, a lot of important metrics are already configured with CloudWatch by default and built into the Lambda dashboard. There are three main categories of metrics: invocation metrics, performance metrics, and concurrency metrics. Invocation metrics are related to the outcome of the invocation. For example, there is a metric called invocation that tracks the number of times the function has been invoked, and the errors metric counts the number of failed invocations of the function. Performance metrics provide details about an invocation, including duration, which measures how long the function runs in milliseconds, and the iterator age metrics, which measures the time it takes for Lambda to receive a batch of records. Concurrency metrics include the concurrent executions metric, which calculates the total sum of concurrent executions at any point in time. In addition to these metrics, CloudWatch also gathers log data sent by Lambda to help you better understand, troubleshoot, and understand issues. Each function running in Lambda will have its own log group in CloudWatch. Let's dive into the world of serverless applications with the AWS Serverless Application Repository. The AWS Serverless Application Repository is a managed repository for serverless applications published by AWS, AWS partners, and third-party developers. These applications make use of Lambda API Gateway and DynamoDB without the need to provision or manage any infrastructure. Developers can browse or search the repository to find the applications they need, saving time and effort. They can also publish their own applications, promoting reuse within their teams or sharing them with the wider developer community. When deploying applications from the repository, developers can specify custom configuration parameters and manage them directly from the AWS Management Console. So whether you're looking to streamline your development process or share your innovative applications, the AWS Serverless Application Repository has got you covered. So are you familiar with the components that make up the AWS global infrastructure? So let's dive into the world of AWS availability zones, regions, edge, locations, and more. AWS availability zones are the physical data centers of AWS, each with at least one other availability zone geographically located within the same area, linked by highly resilient and low latency private fiber optic connections. Regions are collections of availability zones geographically located close to one another, allowing for low latency connections. Every region will contain at least two availability zones. Edge locations are AWS sites deployed in major cities across the globe, primarily used by end users to reduce latency for accessing services. Local zones are a new type of infrastructure deployment designed to place core AWS services near highly populated areas that do not already have an AWS region nearby. Wavelength zones are embedded within 5G mobile broadband networks that are deployed within the data centers of large telecommunications providers. Understanding these components is crucial for deploying services on AWS. So stay tuned for more insights into the world of cloud computing.